vibration is a harmonic motion, or motion that goes back and forth either side of a neutral or stationary position. In this case here, we have a very basic machine which consists of a mass on a spring, and it is moving back and forth on either side of this neutral position. And it is, if you look at the trace of the red line on the right hand side here, it is following the motion of that mass, but over time. So you can see how this motion, it represents the motion of this vibration over time. The other aspect of vibration is that it is a response to an excitation of a force or a force. This could be either internal or external. If there was no excitation here, this mass would just be hanging there in the spring. It wouldn't be doing anything. But if somebody were to take that mass, pull it down, and let it go, that would be the excitation force, and then the system responds accordingly. Now, what happens if we were to, for example, take that spring and make the coils twice as thick? That affects the system in that it makes it a lot stiffer. And if you think about if you've ever played with a spring before, how would that respond if its stiffness were changed? The It would probably bounce a lot faster. Then the amplitude might be shorter. What happens if you change the mass on the end here? What if you made that mass twice as big, but kept the spring the same? Then that system would respond differently. It would probably bounce a lot slower, up and down. Or right now, this spring is hanging, or this mass on a spring is hanging in midair. What if we were to put this in a tub of water and pull the mass again? How would that respond? And those are examples of some of the conditions that will affect how vibration responds. So things like mass, stiffness, and damping will all affect how a machine or a system or anything that vibrates responds to that force, that exciting force. So a large machine versus a small machine, a shorter machine versus a longer shaft, damping, for example, in an oil film or a sleeve bearing, if the oil viscosity changes, for example, that'll all those things will affect how those machines respond to vibration. The other thing to keep in mind is that these conditions are not always symmetrical around the machine. Take an example of a machine that's sitting on a tall pedestal, for example, a tall concrete pedestal. In the vertical direction, that's going to be very stiff. So it's going to have, if you put a transducer on the top of that, it's going to respond in a certain way. If you put a transducer in the horizontal direction, it's going to respond very differently because the stiffness is going to be much lower in that direction. So when deciding where to put sensors and what type of sensors to put on, always take into account the machinery itself and how it's mounted and what its properties are. We'll talk some more about that later as well. Now, what causes machines to vibrate? It could be any number of things here. I could go through this list, but it's a dry list, and it's things that you will likely have seen already: imbalance, eccentricity, misalignment, looseness, rubbing, etc., etc. Main thing that I want to highlight for this slide in this moment here is that vibration is almost always a symptom of something else. Vibration itself, while it can cause issues, if it's vibrating too much, things will fall apart. That's very loud. While vibration itself can cause issues, mute everyone. Hopefully this will take care of that.
I muted everybody. You might have to unmute yourself,
I got it.
Derek.
All right.
Okay.
Um, so yes, while vibration itself may cause other issues, the initial vibration is likely a symptom of something else. If you get some dirt buildup on a fan blade, or bolts come loose, or something like that, the machine is going to respond very different, or is going to respond differently. And chances are it'll probably respond by vibrating more or less, depending on the issue. But a change in vibration is a symptom of something else. And how a machine vibrates also depends on the type of machine that it is and the type of bearings that are on that machine. On the left, we have an example of a sleeve bearing or an oil film bearing. And on the right, we have an example of a rolling element bearing. If you were to trace the path of the center line of those shafts, the path would actually be the same. But because the left bearing has an oil film to move within, the machine overall reacts very differently than the one on the right, which is constrained by those rolling elements and is thereby forcing the entire machine to move. So these are also considerations of what the vibration is going to look like, and will also lead to how you choose what sensors to use on those machines. And of course, when the vibration gets too bad, well, then things get very bad. And hopefully, by understanding the fundamentals of vibration, what it is and what it means, and how you can track that vibration, whether it be trending it, alarming it, etc., we can hopefully help you avoid catastrophic situations like this. All right. The, the following presentation, we're going to break it down into three major parts. First, we're going to be talking about vibration characteristics, how we talk about vibration, what some of the vocabulary is, what are some of the characteristics that we use to describe vibration. Then we'll look at the units of vibration measurement and how they're different. And then finally, we'll wrap up with a discussion on different types of sensors and how those relate to the previous topics. The sensors discussion at the end of this is intended to be just more of an introduction. We're not going to get too deep into it. We have future topics planned that will dive much deeper into vibration sensors and when to use them and how to use them and how to apply them. But hopefully this will give you at least a good understanding of things to move forward with. All right, vibration characteristics. There are four main terms or descriptors that we use to describe vibration. We can talk about the amplitude, how much it moves back and forth. We can talk about the frequency, how quickly it moves back and forth. We can talk about the phase, which describes the shape of the vibration. And we can also talk about the shape and form of the vibration. Of these four, three of them are quantitative items. So it's those first three. By quantitative, I mean that you can actually put a number to those. And anytime you can put a number to something, you can trend it, you can monitor it, you can alarm off of it, you can compare it to other things. You can compare amplitude or frequency or phase to other things like pressures and flows and temperatures, whatever else might be affecting the behavior of that machine. The shape and the form, while not necessarily quantifiable, it's more of a qualitative thing, is still can be still very, very important, particularly when you're getting into the diagnostic side of things. And as such, it's important that you have the right tools available to yourself to be able to be able to look at that form and analyze it and compare and see how it changes over time, et cetera, et cetera. Things like our System 1 software or Adre software or portable data collectors will all give you a view into the form and the shape and form of the vibration, as well as gathering those quantifiable numbers as well. And first up, let's talk about amplitude. So amplitude being the measurement from the top of the vibration to the bottom of the vibration, or that cycle that's telling you how much it is. So vibration amplitude is an important indicator of a machine's condition. It's not necessarily the most important indicator. It may not, and it's definitely not the only indicator of a machine's health, but it is an important one, and when combined with other tools, provides a robust way of keeping an eye on your machines and making sure that they're behaving the way they're supposed to. The greater the amplitude, the more severe the vibration. This goes without saying, but it's important to note. And we at Bentley, Nevada, we refer to the overall vibration, or another term that we use, particularly in our software, is the direct amplitude. That is the unfiltered trending parameter. So if you look at that raw vibration waveform with all the noise and bits and pieces in there, the overall vibration is the direct amplitude. Once we take that and filter it down, we'll also look at the amplitude, but those would be the filtered amplitudes.
Derek,
Yes.
there seem to still be some folks who are having trouble seeing the presentation. Somebody put in that for the people who didn't see the slides at first, they had the same issue when just using their web browser. They downloaded the Teams app and it worked fine. So you may have to download the app and join that way. Other than that, neither of us are all that familiar with Microsoft Teams yet because we just got this tool recently. But what I found is in the upper left corner, you may see a screen, and if you click on that, it'll show the presentation. Okay. Back to you, Derek.
Excellent. Thank you. All right. So for overall amplitude trending, so machine problems can be detected using overall vibration trends. Particularly if you compare those, it can be a simple form or rudimentary form of analysis, comparing an increasing or changing vibration amplitude with other process parameters like temperatures and flows and pressures and whatnot. You can do some basic analysis, but being able to take that overall vibration amplitude and really break it down more and dig into it deeper is where the real value of diagnostics comes in. And we'll talk a bit more about that coming forward. And of course, preset alarm levels can be applied. So if you look at something like this is a simple trend plot. We've got a couple of parameters on here. And in Bentaly, Nevada hardware, typically we offer alert and danger set points. These are often recommended by OEMs or just from your past experience, knowing how your machines react. The alert is generally set to give you a heads up that something is getting really bad and that, imminent danger or failure may be possible. And the red is generally set as a protection set point. This is where if it goes above that red line, you ideally want to shut the machine down very quickly. Otherwise, you run the risk of losing material, losing products, or even harming other people. And that's what we want to avoid. But machines do respond differently just over time. In this particular example, the customer had been keeping a close eye on his process and noticed that every now and again, the machine would run pretty steady, but then it'd start to vibrate a lot. It wouldn't quite reach the alert set point, so the operators didn't see that it was happening, but he noticed that this was going wonky here. So what we did was we added another software alarm here, a lower alarm. The operators aren't going to see this unless they're looking at the software, for example, System 1, but as a diagnostic engineer, this was very valuable to him to know when this machine was exhibiting this strange behavior, and he could start to correlate it and figure out what the root cause is. All right, next let's look at frequency. So frequency is a measure of the number of complete cycles in a specified period of time. And if you look at the units that we use to describe frequency, some of them kind of give you a clue to that. So CPM, for example, cycles per minute. So if you take this, look at this vibration trace here. This is a nice clean sinusoid. It's rarely going to be this clean. But if we look at this, we start at the top, we go down, we come back up. That is one complete cycle. When it starts to go back down here, that's the start of the next cycle. So if we take that one cycle and we measure how long it takes to go from start to finish of that cycle, that tells us how quickly this particular vibration trend is moving or cycling. So CPM is one way of describing that. Hertz is another very common unit of measurement for frequency, and it is simply cycles per second instead of cycles per minute. Hertz is a very common frequency denominator, but cycles per minute is very useful because it correlates very easily to RPM, to rotations per minute. So if your CPM is the same as your RPM, that means your machine is vibrating at the same frequency that it is rotating. So that is easy to correlate. And even easier is if you can track that. So if you have a phase reference, if you can track that speed and compare it to the vibration frequency, we actually call that NX as a frequency measurement. So N standing for multiples and X is multiples of running speed. So if your CPM is the same as your RPM, we would call that 1x. If your CPM is twice your RPM, so if the vibration is happening at twice the frequency of rotation, we would refer to that as 2x, and so on and so forth. If you got, as an example here, if you have, say, in this, funny little example, if you got 3 blades on a machine, it'll cycle, you'll pick up that blade passing frequency 3 times every rotation. So this would be 1, 2, 3x vibration. Imbalance typically occurs at 1x. Bearing faults happen at a fairly high multiple of running speed. Looseness is a different one. There's many different fault frequencies that can show up and affect the overall vibration amplitude here. This is an illustrative example of a very messy, but perhaps more realistic waveform that you might see out in the field. But now if we take a waveform that's, messy like this, you can see you kind of squint at this and look at it from a distance, you can see that there's a general form here, but it's not a nice clean sinusoid like we've been looking at. You see that there's other frequency content in here. So how do we describe that? Well, thankfully we have software, so we don't have to do it by hand. But effectively, what the software does is mathematically, it looks at different frequencies and then you can break it down. So this is looking at one particular frequency, so it's a nice sinusoid. So this would be, I'm guessing this is likely going to be a 1x. This is at running speed. That's generally where you're going to see the most amplitude. And going forward here, uh, as the frequency increases, you'll see other amplitudes going along here. So looking at it from this direction, we're still looking at it in the time domain. We're seeing how this vibration moves over time. But if we were to look at it from the other direction, we're now looking at it in the frequency domain. And if you take each of these amplitudes and lay them out over the frequency as we've done here, now you see what we would call a spectrum or an FFT plot. So here where we have that first large amplitude, this could be an indicator of imbalance, and it would likely be labeled as either 1x or 60 hertz or 3600 CPM for a 3600 RPM machine, something like that. The bearing defect would be a higher frequency, you both might see some sidebands there, and gear mesh would yet be a different frequency, depending on the geometry of the machine, number of gear teeth, diameters, etc., etc. So being able to take a waveform and mathematically break it down and represent it in a different form can give you valuable information. Is one better than the other? I wouldn't say yes or no. They each have their usefulness, and it's you definitely need to have both of them to get a complete picture of how the machine's operating. Certain types of applications will tend to be more spectrum focused. For example, rolling element bearings are typically more spectrum focused, whereas sleeve bearing applications are generally more waveform focused, where things like the waveform and the orbit are more useful than the spectrum itself. Next, let's take a look at phase. The phase of vibration is measured relative to a reference signal operating at the same frequency. So in order to be able to compare two signals, they need to be operating at the same frequency or filtered to that same frequency. And we'll look at what that looks like shortly here. Phase is usually used to describe the NX or a synchronous vibration vector. So again, when you filter that complex waveform down to one particular frequency, phase is then used to describe that frequency and describe how it's behaving. And a tracking filter can be set to track the NX vibration, whether it be 1x, 2x, 3x, 6x, whatever. Track that NX component at varying machine speeds. So the most common example likely is going to be tracking the 1x amplitude and phase during run up and coast down. That gives you a whole wealth of information as to where the heavy spot is, where your resonances are, if there's other things, if that behavior is changing over time. That is incredibly useful information in addition to the overall vibration amplitude as well. And when we look at describing phase, it's the units we use are degrees, so from 0 to 360 degrees. But let's look at one example here. This is a very simple shaft. Hopefully you don't have shafts that are moving quite this much, but for illustrative purposes, hopefully it's more legible. So we have a transducer A on the inboard side and B on the outboard side. And they're both in the same plane and they're looking at the same shaft. In the first example, you can see that as that moves around, that bow shape moves around, when the shaft gets closer to A, it gets closer to B at the same time. And likewise, when it moves away from A, it moves away from B at the same time. So if we were to trace that behavior over time, we would see that it looks like this. So you can see that they're moving together. And we would describe that as having a 0-degree relative phase, or another way of saying that is being in phase. In contrast, here the A probe, when it sees the shaft coming closer, it sees the B probe moving farther, and vice versa as that shaft rotates around. So the traces would look more something like this. So as the A probe moves away, the B probe moves closer, and vice versa here. And we would describe those as being 180 degrees of having 180 degrees relative phase, or being out of phase, fully out of phase from each other. Now, what happens when we've got two signals that are not quite that clean? Well, we can still do the same sort of exercise. So first, we define one complete cycle. So in this case, I've chosen to use from peak to peak here. You could do from crossover to crossover. Really, it's up to you, dealer's choice. But I'll start from the peaks here, and then I'll compare this peak relative to that peak. So if we compare those, I can see here that this signal is actually crossing over right as this one is at its peak. So that is about a quarter of a full cycle, which tells me that this is going to be about 90 degrees. So that is relative phase, comparing two vibration measurements to each other. Where would we use something like this? It's actually quite common when you're looking at a machine that's out in the field and you want to look at, say, the inboard versus outboard bearing, and you want to see how they're moving relative to each other. Is this machine rocking back and forth together? Is it wagging? Is there a node in the middle and the bearings are moving opposite each other? By putting a sensor on the inboard and the outboard, or the drive and non-drive end bearing in the same plane and comparing them, you can get a good sense of that relative vibration between the two, and it gives you a great description of how that machine is behaving. But a more common, at least for us in the Bentaly, Nevada world, the more common use of phase is going to be absolute phase. And this is where we use a phase reference signal. And our term for it is key phaser. So somewhere on that shaft is going to be a notch or projection with a prox probe observing it. And as that notch or projection goes by, it creates a sharp signal, sharp reference signal here. And that is then applied to every other vibration signal in that rack or on that machine train. So you can see here that this is the same sort of vibration signal we had in the previous slide, but now we have a little blank bright occur every time we have one of these references go by. And what that tells us, every time we see a blank bright from one to the next, that is one full rotation of the shaft. So this is one rotation here, and then this is going to be another one, and so on and so forth. And what we can then do is we can use that to measure the absolute phase. So in this case, again, as before, we start with defining a full rotation. Now we don't have to eyeball the peaks anymore. We have a physical measurement of that reference there. So from here to there is 360 degrees. And from there to the first positive peak is our absolute phase measurement. In this case, it's going to be about 130 degrees. Another thing you can do just from eyeballing this particular frequency here, you can see that from key phaser dot to key phaser dot, this is one whole cycle of vibration. So now we know that if we get one cycle of vibration for one cycle of rotation, that tells us that this signal is a 1x filtered signal. If I were to see two complete cycles of vibration for every one rotation, that would tell me it's a 2x signal, and so on and so forth. This is a little video that goes through and illustrates what things look like in reality. And so we'll talk through it as we go. So here you can see in this case where the key phaser probe is observing a notch in the shaft, and the shaft is rotating in the bearing. Hopefully your bearings don't have quite this much clearance. But first we're going to look at the Y sensor here. So you can see here that as that shaft goes farther and closer away, the trace on the oscilloscope down here shows that waveform going up closer and farther, closer and farther. And now we stop, we pause. Okay, so when it goes past that notch, it marks this as the 0 point for our reference. Now we can see how long it would take to get that first positive peak. So it rotates around. That's when it's closest. That's the first positive peak. So from where it triggered to where it's the closest, that's our measurement. And that is 135 degrees in this particular example. So what happens if we look at the X probe? If you think about it, the mathematics is going to be very similar. So we're going to take that X probe and do the trace of it. As that shaft moves closer and farther away, the same sort of thing happens. But you'll notice that the trace is different here. So there, as the key phaser triggers, it's not going to take much rotation for the shaft to get close to that X probe. It's a much shorter rotation than it did for the Y. In this case, it's about 45 degrees. So now when you look at those together and you compare them, we've got two numbers there. For the Y probe, the absolute phase is 135 degrees. And for the X probe, the absolute phase is 45 degrees. If you take that and you compare the two of them, you'll notice that the difference in phase is 90 degrees from each other. A common question that I get is, okay, well, that kind of makes sense, right? The probes are 90 degrees from each other. Therefore, the relative phase should always be 90 degrees from each other. And at first glance, it kind of stands to reason. But that is only applicable in one very specific scenario, and that is when the shaft is rotating in a circular orbit. So here you could see that that shaft was rotating around very nicely in a very round orbit, and therefore the relative phase between those two probes is 90 degrees. If the shaft is moving in a more realistic orbit, which is generally going to be more elliptical in shape, you're going to have different relative phase between the X and the Y probes. And understanding that will help you see when you see the orbit, it'll work there. We don't get too much into that here, but I just wanted to bring that up as it's a common question I've gotten as I've taught other webinars on this. And when is vibration phase used? In a variety of places. Very commonly in imbalance. When you're doing balancing, it's important to know how that system is behaving to the heavy spot in the system, which then helps you define where to put your balance weights so that you can balance it out. Also helps for tracking misalignment, resonance, etc., etc. And perhaps one of the most important ways that absolute phase is used is for tracking change. If a system is operating under steady state conditions, steady process conditions, ideally that phase shouldn't really change. If you do notice that everything else is constant but your phase is changing, pay very close attention. Something in that system is changing and that shouldn't be. Whether it be stiffness, whether it be the mass, sometimes something like buildup or something like that could be changing the mass of the system, or even the uh, uh, totally blanked. Anyway, changing conditions. Phase is a good indicator of that. And if you have a good sense of the history of your machine and you can track that phase, you can also put banding alarms on that. That's not necessarily something that an operator needs to be concerned about and see a bright flashing red light when the phase is changing. But as a diagnostic engineer or mechanical engineer, that can be a very useful early heads up that something is shifting that you need to pay attention to. Moving right along, vibration units. So now we've described in general terms how we describe or how we reference the components of vibration. Now let's look at the different measurements of vibration. So first off, we have displacement. So displacement would be defined as the total distance traveled from one extreme to the other. So again, going back to our very simple machine example here, As this mass goes back and forth, we can measure from the top of that cycle to the bottom of the cycle. That is how far this machine has moved in total. And we refer to that as peak to peak displacement. So when measuring displacement, we always refer to it as peak to peak. The units used for this are the same units used for distance measurement. So at the scale that we're generally working at for vibration, it's going to be microns or thousandths of a millimeter, or thou or mils, which are both terms that we use to describe thousandths of an inch. Depends if you speak metric or imperial. But you need to be able to, when you're describing displacement, include the units and the peak to peak as a reference here. So that is displacement. Next, we have velocity. So velocity describes the speed at which displacement occurs. So how quickly is this moving back and forth? If you think of this example, at the top, it almost pauses, and at the bottom, for a brief moment, it pauses before it changes direction. So at those moments, the velocity of that system is zero. And as it's going through down the middle here, that's going to be the fastest point in that cycle. So if we were to trace this velocity path, you can see here at the top and at the bottom, the velocity is zero. Whereas at this part of the cycle or that part of the cycle, velocity is maximum. Um, and when we describe velocity, we use either zero to peak or RMS to describe the amplitude, and the units we use are millimeters per second or inch per second, again, depending if you're metric or imperial. I will comment here that I've got these waveforms as similar amplitudes purely for illustration's sake. The displacement amplitude and the velocity amplitude are never going to be the same, unless, I know, maybe there's a rare scenario where that might be the case, but they're going to be very different numbers depending on how you measure things. So I'm only doing this for an illustration's sake to illustrate the relationship between them. Finally, we have acceleration, which would be, of course, the rate of change of velocity. So if we think about this, the displacement curve, almost like a roller coaster ride, when you're zooming up the roller coaster at the top as you turn around, or if you look at it from the top down as if it's a race car on a track, on the straightaway, the race car is moving pretty constantly, but as it goes around the corner, you're going to be thrown into your seatbelt, and that's going to be the maximum acceleration. And as it goes along at a constant speed, this will be the minimum acceleration on the straightaway, but then as you go around the corner again, you get the maximum acceleration around that corner here. So if we were to trace that acceleration curve, you would see that it's basically out of phase from the displacement curve. Again, we describe this as either zero to peak. So we start from the neutral up to the peak. So that's either peak or RMS. And the measurement units are Gs, or inch per second squared, or meters per second squared. G's standing for gravity. So when we look at this again, displacement, uh, velocity leads displacement by 90 degrees. And acceleration in turn leads velocity by 90 degrees, or leads displacement by 180 degrees. Uh, the main reason that, generally speaking, you're not going to use this relationship, this isn't going to affect your life very much. But if you happen to be balancing a machine and you're not able to use proximity probes, if you're using case-mounted probes, you do need to take this into account, as the phase gives you an indication of where on that machine shaft you need to be able to put your balance weight. So this phase information is going to be useful there. But generally speaking, day-to-day life, this isn't going to affect you much. However, the relationship between displacement, velocity, and acceleration in terms of sensor selection, which we're going to get into next, is very important. So if we look at this from left to right, this being lower frequency and right being higher frequency, if we assume that a machine is vibrating at a constant velocity, just because that is the middle ground there, at a constant velocity, something's moving back and forth. The displacement at lower frequencies, that displacement is going to be much higher, and that acceleration is going to be very low. Conversely, at higher frequencies, if that machine is moving at a constant velocity back and forth, The acceleration is going to be much higher, but the displacement is going to be much lower. If you think of being able to hold a mass in your hand, or some sort of a weight in your hand, if you move it back and forth a lot, um, at very it's you're not going to be able to move it at a very high frequency. Whereas if you can move it very small, if you move it back and forth a short distance, you'll be able to move it a much higher frequency. So this relationship starts to help us understand when and why we apply different types of transducers measuring vibration. So we have a couple of different transducer types, and each of them has an application that it's applicable to its characteristics and construction. So first off, let's look at the proximity probe. This is Bentaly, Nevada's bread and butter. This is where we made our name, and this is proximity probe. Is the probe itself is mounted in a fixed location at a fixed point, and it looks at a target surface relative to that fixed point. The most typical example of this is going to be on a bearing. So the probe is going to be mounted in the bearing housing, and it's going to be observing what the shaft is doing relative to that bearing housing. As such, this is very applicable for fluid film bearings, where the shaft is able to move relative to that bearing housing. The proximity probe is capable of very low frequency response, literally down to 0 hertz, which is where things like thrust position come into play, when there isn't really a vibration per se, but there is an absolute distance from the probe to the target surface. So proximity probes are very versatile in that regard. Again, also typically better used at lower frequencies where displacement is going to be displacement response is going to be much better. The units, to recap, is going to be in microns, or thousandths of a meter, no, thousandths of a millimeter, or micrometers there, or thousandths of an inch, or mils, thou or mils. Looking at an example here on a machine, here we see the probes mounted in 90 degrees from each other. This gives us a nice full 2-dimensional picture of what's going on in this particular plane. And here, for this ideal example, the bearing housing is fixed in place. It's not moving at all, but the shaft is moving relative to that bearing housing. And these probes are able to observe that distance from the probe to the shaft. And as it moves farther away and closer back together, each one of those provides a picture. When you combine those waveforms, you get this trace in the middle here, which we call the orbit. Next up, we have velocity transducers. These have an inherent output of velocity units, and these are case-mounted sensors. As you can see, each of them has their own form of a threaded tap or threaded mount at the bottom, and you'll drill and tap the machine casing and mount this on there. And when compared to proximity probes, the difference is critical. That whereas a proximity probe, again, measures the movement of the target surface relative to the surface the probe is mounted on, velocity transducers only measure the movement of the casing itself. They don't give you any indication of how that shaft is moving relative to the bearing housing. They only tell you what that casing is doing. And given that the velocity transducers, they have the output and velocity, they're good for that middle range of frequencies, somewhere in that 10 hertz to 10 kilohertz type range. And generally where we use these, or where we see these applied, is places where you're interested in the mechanical behavior of the machine. And by mechanical, I mean things like imbalance, misalignment, looseness, that sort of thing. Oftentimes used for protection if casing mounted is the only option available. Um, I show here an illustration of an older style which is still around and still has its uses, which we call the moving coil seismoprobe. In this case here, the case of the transducer has a fixed magnet, which is, as you can see there, it's threaded and fixed to the case. and then it's got a coil of wire hanging by springs at the top and the bottom. And since this case is fixed to the machine, as the machine vibrates back and forth, uh, this magnet is going to move with that casing. But because the coil of wire is mounted on springs, due to inertia, it's going to want to try and stay in place. So it's going to move relative to that magnet, and the output is in velocity units. Um, that's moving coil seismoprobes. They're important to note in terms of from mounting considerations. There's some challenges there, and just the fact that it is a moving part means that it has a finite lifespan and should be checked regularly just to make sure that things are still working the way you expect them to. All the other sensors here are what we at Bentley, Nevada refer to as velometers, which is essentially it takes accelerometer. There's an accelerometer guts in here, and then there's a little board there which takes that velocity signal, sorry, acceleration signal, and integrates it to velocity to give a native velocity output. So these are what we call velometers. And as mentioned before, the most typical application here is going to be machines where you're interested in the mechanical movement. So in this case, it's a sleeve bearing, but just due to the stiffness of the machine or the size or whatever, that casing is also moving. And if we aren't able to put a proximity probe on here, a velometer is basically going to be the next best thing. This would be one place where we recommend having velometers or seismoprobes. And finally, we have accelerometers. Uh, these are uh, the construction of these is such that they've got a little piezoelectric crystal mounted and fixed to the frame of the Excel. And on the other side of that piezo crystal is a mass. So again, since this is mounted on the machine, as that case moves up and down, um, this mass on this other side here wants to stay in place. So as that mass moves relative to the casing, it puts a stress on that crystal, which produces a little electric charge, which we can then measure, and that outputs a native acceleration unit. Again, that would be meters per second squared, inch per second squared, or standard gravity, or G's. And based on the design here and based on the capabilities, accelerometers are very good for high frequency applications. So if you remember, think back to that sort of X shape. At the higher frequency applications, acceleration is going to have a much better response than velocity or displacement would. So for high frequency applications are things like gearboxes, looking at that gear mesh frequency, or rolling element bearings, looking for those bearing fault frequencies, inner race, outer race, ball spin frequencies, and so on and so forth. Those are applications where acceleration is the right unit of measurement to use. So again, looking at an example here now with a rolling element bearing. Just for the sake of argument, if you were to take a proximity probe, mount it on that bearing housing, and observe the shaft, you would essentially see zero. Because of these rolling elements, the movement of the shaft is directly translated to the bearing housing. So there's no relative movement between the shaft and the housing. So proximity probe is useless in this location, in this application. However, an accelerometer is ideal here because it'll measure the bearing housing movement, but because of its high frequency sensitivity, it'll pick up any issues here. So if there is a fault on the outer race, as an example, as each of those rolling elements goes by, the accelerometer is going to pick up that frequency as it goes ping, ping, ping going by there. And even more so, if you think of even higher frequency, if you think of each of those little rolling elements going past that defect as a tiny little hammer hammering that housing, you can almost imagine a little ping noise going out, ping, 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 and that ping noise is going to be that high frequency noise is going to show up very early in defect life. And accelerometers can pick up that very high frequency, and with the right sort of measurement and the right sort of processing in a monitor, we refer to it as enveloping, there's other terms for it. You can pick up those very high frequencies and get very early indication of bearing health degradation. So that's why accelerometers are very useful. And one more scenario I want to mention for those that are in the, particularly in the power gen business or anybody with like a large steam turbine generator where things are very massive but still using sleeve bearings. There we have something that we call a shaft absolute measurement. So in this scenario, the shaft is moving relative to the bearing housing, but the bearing housing is moving as well. So just one technology alone, whether it just be just proximity probes or just velometers, are only going to tell you part of the picture. But by combining those technologies, by taking that velometer, you take that signal, you integrate it to displacement, and you relate it to that proximity probe. They need to be mounted in the same plane and compared to each other. But by comparing that velometer signal to the actual proximity probe signal, we can now get a sense of how the shaft is moving completely independent of that bearing housing. So that is, and this is generally going to be for larger machines with a very large shaft, and relative to the size of the shaft, the bearing housing just can't be big enough to damp out or to eliminate the bearing housing movement. So hopefully you found that interesting, and hopefully you found that useful. Please, I don't see any questions on Slido yet.